Hello. I thought it could be cool to talk about how to generate random numbers in a general sense, and then also we can make some C++ code to do it. So the place to start is, okay, what's a random number? It's some number you grab from a distribution. And maybe you have a uniform distribution, which would be like, let's get drawing to work from, let's say 0 to 1. We grab some numbers, and we randomly grab a number, and the probability of any of these numbers is the same as this one, as any of them. But we could do something more interesting with like a normal distribution, or Gaussian, which would look something like we have x, and the probability of getting that sample at that position x, and it looks like the bell curve. Try to draw it symmetrically. And what this basically means is samples closer to the middle here are more likely, and getting a sample farther away is very unlikely. Like here is super unlikely. And most programming language gives you this guy, the uniform random number generator, where you get a number between 0 and 1 uniformly, or 0 and whatever number uniformly. But if you want a normal distribution, maybe that's more complicated. Or maybe you even have something more fancy, like maybe your distribution looks like that. We have some function that looks like this, and it's like more likely to get numbers here, here, a little bit here, and here, and then outside it's like 0, like here and here. You shouldn't find any numbers. And something like this is going to be, you're not going to have that included in your standard library of number generators. But we're going to look at something like this normal distribution because it's more familiar as an example. And the way to think about this is we need to somehow map this, which is what we start with, the uniform, to this. And like I said, that basically means numbers in the middle here are more likely and numbers towards the outside are less likely. So one way to do this is, let's kind of draw this a little bigger. Excuse my drawing skills, they're not perfect. X, P of X. And what we can do is basically first grab a number between, or somewhere in the domains of x along the x-axis of our function. And we can say for this normal distribution, maybe outside of these points, it's basically 0, no chance of getting anything, so that will be our range. So we randomly grab a number. I'm actually going to move this a little bit down. So we randomly grab an x point, let's say here, and then we look at the corresponding y value over that distribution, so that would be right here. And then we draw a line above our distribution. It's got to be above it at all points, so let's say here. And then we sample along this line. From here, different color. From, let's say, here down to here. And if the point we grab uniformly, we grab along this line, is larger than our functions, let's say it's here, we don't accept it. In that case, this x number we drew, we don't keep. But if it's less than our probability distribution, so let's say it's here, then we do accept it. And what this basically means is, maybe we can draw the steps so it's more clear. First, grab an x point, grab uniform x point, 2, plug in x into P of x, so we get this point here. Maybe we can put some labels. So this would be blue, this can be green, and then 3, we get another random sample, get another uniform sample, see if less than our function, p of x. And what this basically does is if we're always going to be sampling between this line, and maybe this is red, if we're always sampling between this line and our function point, then when our function is taller, let's say in this region, then a uniform number can be anywhere along this line, it can be anywhere along here, but more of the line is going to fall below our function. More of this line, you can see like this is maybe the halfway point. So at this halfway point, you're like 50-50 above or below the line, but we're clearly above that, so we're more likely to get a point in our function. But let's say we drew a point, our x point here, and then we drew our uniform line. Maybe we can draw a bit better, maybe not. No matter what value we grab along this line, it's going to be pretty much always taller than our function, so we should never grab a point from over here. And that's kind of the idea here. We want to grab points proportional to the height of our function. So going back to this kind of weird function over here, this would mean, we can walk through another example. Let's say we grab at point x here, we draw our line, and the line's always the same. Just it has to be above our function. There's going to be no point along this line that's going to be smaller, because this point is basically 0. So we're never going to grab a point here. Let's say we grab another point randomly, I don't know, here. And then we draw our line, and we uniformly sample along it. Most of this line is below the function here, right? So we're more likely to get here. And so proportionally, we're going to get more points where the function is higher, like here, and here, and here, and here. And then when the function is very small, like here, we're not going to really get any points there because the function is so small that when we sample along this line, we're not going to grab a point ever that's going to be smaller than that. So that's basically the method. It's called rejection sampling, and it's a quick method to get a probability or sample from our probability distribution that we don't have a number generator for. So we can actually code this up in C++ really quick, hopefully really quick anyway. And right now I just have just a basic starter C++ file, and I'm going to use raylib, which is a nice library for visualization. If I run this function, all it does is, or run this code, all it's going to do is just make a little blank box for us. So following our rules from before, let's say we want a Gaussian number, the Gaussian random distribution. We first need to kind of define the function. So let's say float Gaussian is going to take in an x value, and then maybe the width of the Gaussian is like some parameter a. So just to be clear, a Gaussian function like this, the function would be proportional. So p of x is proportional to the exponential minus a x squared. So when a is a really big number, let's say a is like 10, our function is going to be very shallow. And when a is, because that basically means this exponential decays really fast. And the height's always going to be 1, because at x is 0, this goes to 1, e to the 0 equals 1, so the height's always going to be 1, and after that it falls off. And let's say a was, let's say 1, it's going to be a lot more broad. And that's also always going to be 1 there, because e to the 0 is 1. So we can do something like that in C++, where maybe we could just default this to, like, I don't know, 3. Why not? And then we can return an exponential of minus a times x times x. And that's our Gaussian function. Why not? Now we need a random uniform number. We can call this float uniform. And then let's say the domain of this, or like range or whatever, is between low and high. So this is going to generate a number between our low number and high number. So to draw this real quick, this would be like this function up here. The low point here would be 0, the high is 1, so we can generate numbers in this range. So to do this, I'll just use like the random built-in in C, which people will say it's not like cryptographically secure, but I don't care. We're not doing cryptography. But just so you know, it's maybe not the best random number generator, but it's good enough for our purposes. So we can say, why not float x is, or the rand function, which grabs a random number. And this is a random number that's an integer, and their max allowed value for that integer is, it's called rand max. So now we have a number between 0 and 1. Number between 0 and 1. And now we just need to map this between low and high. So we can basically just, the difference between these two is going to be the kind of width of our number, and then the starting point is low. So float r for a random number is going to be low plus x times high minus low. So this basically is just mapping 0 to 1 to high to low. So for example, if x is 0, then this whole expression is 0, and we're just at low, which is, let's say, 1. And let's say x is 1, which is the max value, then we get low plus 1 times high minus low. So low minus low is 0, so we're just left with high. And anything in between is between low and high. So we can just return r. So now we have a uniform. Great. Maybe we can call this u for uniform. Why not? I don't know. Next, we need a function to do this rejection sampling. So we can say float, and rejection sampling is really for our, let's say, our Gaussian number. So we can say random normal, because a Gaussian and normal is like the same, just a synonymous name for Gaussian. And we can say the input parameters are really just float a, the width of our Gaussian. So to do this, we can look at our steps again. First, we grab a point along the x-axis, and to encompass all of the Gaussian, we can make our low point and high point like much bigger than a. So we can say float low is going to be like minus 20 times a, so way smaller. And float high is 20, and we should make these floats, point f for float, times a. And then we can say float x, which is our point along the x-axis, is going to be a uniform between low and high. So now we have a float, and now we want to see, is this float below our function? So recall our function maximizes at 1. So we can really draw this blue line. It doesn't have to be up there. It could be just right here. Maybe I'll draw that in blue to be or no, it's fine. We have this line here. So if our function is right here, it's always accepted. If it's here, a little less accepted, here, never accepted. And this is still fine because it's all proportional to this function. So the numbers are going to be in that distribution. So we can say float y, which is our Gaussian, is going to be Gaussian x and a. And then we want to say if, now we need one more. So we need another sample along the line, this line, and if that sample is below our point, then we keep it. So we can call that our float line value equals uniform between 0 and 1, because our Gaussian goes between 0 and 1. And then if line value is less than y, we can return x, because that means this x value we got is from our Gaussian distribution. And if it doesn't, we need to run this again until we get a random normal, because the user is expecting, hey, give me a random normal number. So what we should really do is run this in a loop until we get a value. So maybe I'm going to put a while loop, which maybe is dangerous, maybe not the best idea, because maybe this runs infinitely. It shouldn't, but hopefully we don't make a bug, and then it won't run infinitely. And then we just do this. We keep running this loop until we get a value that's acceptable, and then we return it. And then if we don't get a value, we're going to run infinitely. And maybe to be safe, we can just make this run only, like make it run in a loop for 1,000,000 or something times. And if it, whoops. So we're running a for loop for however many times, 1,000,000 times. And if it fails, we can return, I don't know, 0. And then maybe print an error message. Error. But hopefully before 1,000,000 times, this thing will return the x value. So, okay. Now we have some functions, and maybe it's nice to actually visualize what's going on. We want to run this and hopefully get some numbers. So one way to visualize a random number distribution is a histogram. And I'm just double checking I'm recording. Yep, I should be recording. One way to visualize it is a histogram, which basically tells you how many times you've gotten a number. So if we have a distribution that looks like this, and we randomly sample along it, we can make a little bin every time we get a number in some range. So maybe we've gotten this number this many times, this number this many times, like in that range. And if we draw a bunch of bins as we've accumulated samples, we get something that looks like it. So for example, the first sample, maybe it's here. So we draw a bin of this height here. The next sample, maybe it's here. And then the next one, maybe it's here again. So now that box is higher, that bin is higher. And the next one, maybe it's here. And we keep doing this process. And over time, we should see that over here, it grows much faster. And over here, it grows much slower. And then the general shape of these bins should follow this Gaussian distribution. So we can do that. Let's make a little class called histogram. And maybe we can have some number of bins and the width of each bin. So we can do a vector of ints, which is going to be the counts, which is the number of counts of each bin. And then we can have, yeah, that's really all we need. And then we need, I guess we need a way to put numbers in the bin. So we can initially, let's initialize this histogram, and we can say that it has a low value, high value, and then int and bins, which this basically means where should the histogram start? Maybe it starts here and ends here, and how many bins should we have along that area? So to do that, we can say we basically need a bin whose size is the high minus low divided by the number of bins, maybe -1. There might be an off by 1 error. So maybe we can have some indexing function to do this. But in any event, when we start this, the counts, the bins, are going to be 0 counts in each bin. So we're going to resize this with n bins, and each bin's going to have the number 0 in it. And then we need some function that logs a new sample. So maybe we should copy down these low and high values. So float low, high. And then we can tell our class, hey, these are the low values to have. And then we can say void add sample, which is, we'll put a sample in a bin. And then we can say float x is our sample. And then also we should know like what is the bin size. So we can call that like dx is the bin size. Bin size. And then float, and then dx is going to be high minus low divided by float, because we want this to be a float, not an int, and bins minus 1. And you can think about that as like the -1 factor. If we have 2 bins between 0 and 1, we should have a bin at like 0.5, let's say. So the bin size should be like 1/2 for 2 bins between 0 and 1. So if bins is 2 and high and low is 1 and 0, then I think this actually, we don't need this -1. So that would basically put a bin at 0 and a bin at 1/2. And if we want our bin centered at these locations, we can, I think just add, we didn't offset. I think this is close enough. It's going to be a little offset from our centers, but I think that's really okay. So we have a low, a high, this is the bin spacing. Now we need to add a sample. So all we have to do to add a sample is basically round the x value into this range between low and high. So maybe we can draw that real quick. If this is, let's say, -5, and this is +5, and there are, I don't know, 10 bins, then at each of these locations they have a bin, and if we get some number like 1.5, we need to round that to the closest the closest bin number. So to do that, I guess we can do, if it's less than -5, we put it there. If it's greater than +5, we I guess if it's less than or greater than the extremes, we shouldn't really keep it. So that's okay. We'll get rid of it. And if it's in the middle of the range, I think we just need to multiply it by, let's work out an example. So if the range here is 10, and we have, let's say 10 bins, then each bin is length 1, which kind of makes sense. A range of 10 bins, each bin should be 1. And then this should be in the like 6th or 7th bin, because we have like -5, 4, 3, 2, 1, 0, 1.5. So that's in bin corresponding to like 2. So what we need to do is, basically I think just move the range. So -5 to 5 should really map to 0 to 1, and then we need to map, or really 0 to n bins -1, and then we need to map, and then once we have our number, we can do that same mapping. So for -5 to 5 to 0 to n bins -1, what we can do is we can call this x plus, or x minus low, which would be -5. So x minus -5, which is plus. So now that the lowest number is 0. And then we need to divide it by the length, which is basically what we did before with our uniform number, I'm realizing. So divide by the length, so divide by 5 minus -5, so 10, and then multiply by the number of bins. This will basically move 0 to 1 to 0 to n bins -1, I think. And if it's off by 1, we'll try to fix that. So, okay, so we have this. So all we do is, we can call it y for the moved into our range number. So it's going to be x minus low plus or sorry, x minus low, that's at 0 now. And then divided by high minus low, just double checking our work. Yep. And then multiply that by float and bins. Whoops. Did we save that somewhere? Oh, counts.size, which is the number of bins we have. So let's see. If we're at the very edge of our range, we should get 0. We should get 0 or n bins, but we don't want to be all the way there. We want to be -1. And then we can make this an int, and then it should be a count. And then just to be safe, we can just make sure, I mean, we can even call this an index, not even a y. We should make sure the index is between 0 and n count. So we can just, if index is less than 0, we should do nothing. Or, cool thing, you can use this for or the word or for or, which I didn't realize until semi-recently. Or index is greater than counts, greater than or equal to counts dot size, which means if we're all the way up to counts, we should do nothing. We should return, do nothing. Otherwise, we can add it to the bin. So counts idx plus. There we go. And then maybe it'll be nice to log which bin has the most counts. So int max count is going to be 1. So and then we'll divide by the max count to kind of normalize this for if we want to draw this, and we don't want to divide by 0. So if counts idx, so if that bin number is greater than max count, then max count is going to be this. Perfect. Great, so that's kind of all we need, and then we just need to draw this. So yeah, let's draw this, or let's set it up. So let's say float a is 3. We need a histogram. Histogram hist, and then let's have it go between like -20 and 20 with, let's say, 128 bins. And then every time we I guess run a frame, let's add a sample to it. So float new sample equals, what did we call it? Random normal. Random normal with a kind of width of a. And then histogram dot add sample, new sample. Hopefully this all works. We'll see how many bugs we have soon enough, or maybe you're screaming in the comments. Then we can draw this. We can call this float bin width is going to be basically our screen width divided by the number of bins. So screen width divided by, maybe we can make this a float. Hist.counts.size. So that's how big each kind of bin we're going to draw is. And then the height is going to be the number of counts divided by the max counts times the screen height. So float screen height times, but this is going to be in a loop because we have n bins. Whoops. So let's actually make this in a loop for int I equals 0, I less than histogram.counts.size. And then the bin height is going to be that. And then, oh, whoops, we should finish writing that. Bin height is the screen height times histogram dot max count. That's like our normalizing factor. And if we wanted to be more efficient, we could save this as like an inverse number, because we're going to do this many times, and division is more expensive than multiplication, but it's really okay for this application. Just thought I could mention that. And then we need the hist.counts for that ith bin. And then, yeah, but then of course in computer graphics we have this like upside down thing. So like the top of the screen is 0, and this is like, actually it's fine, we can just draw a rectangle. We just need to know the height. So that's our height. It's the screen height times this, and maybe we can like times 0.8 plus, I'm just offsetting this from directly the top and bottom of the screen, because maybe that's a little nicer. So that's just the bin height. We just make it a little smaller, and we can do draw rectangle, I think, with the x position of, maybe we can call this float. Whoops, float bin x is going to be float I times bin width. And this will be all the way to the left side of the screen, but whatever, it's fine. You'll get the hopefully like close enough idea. And do I have this upside down? So we have this. So when we get to I goes to counts goes to 1, this goes to, oh yeah, this goes to screen width. Okay, so we have the bin x position. The y position is going to be, let's call it 20, why not? And then, or maybe it's screen height times 0.1 to be a bit more nicer. Yeah, I think that'll go nicely with that. And then the width will be bin width, and the height will be, I don't know, bin height. Bin height, and the color, I don't know what color, gray? Is there a gray? I think there's a gray. Gray. And let's see how badly this works. It's probably not going to compile, but we'll see. Oh, it looks like we're getting a Gaussian, just kind of upside down. So maybe this worked. There you go. Let's actually correct this. Maybe not between like 20 and 20. Let's call it like 10 and 10. And then I think we drew this upside down. So the height, I don't know how we messed that up so bad. Oh, I think it's because of this. The y position's all the way at the top of the screen, so this should be like screen height. I think if we do 0.9, that'll be at the bottom, hopefully. Nope. Let's see, draw a rectangle, x position, y position. Maybe we make this negative? We'll find out shortly. My mumbling, fumbling. Nope. Man, what have we done wrong here? 0.1, that. Okay, let's click on the documentation. Go to definition. Draw a color-filled rectangle. Okay, so I would think x and y is some position. What if I just make this 20? Just hard code it. And then bin height. Let's give it a shot. What did we do? We messed it up. X, Y, width. Bin width. Hopefully X, Y, bin width. Oh, now we forgot the height. Bin height. It's still upside down, but it's looking nice and Gaussian, which is cool. I really would like to figure this out. Let's see, I guess it's starting here. Maybe it's starting here and it's drawing up. No, it should be starting here and drawing down, but why is it drawing down? X, Y, width. There's another coding channel on YouTube and he's always debugging his stuff and I love it, so I figured I can leave this debugging in for fun. Screen height counts divided by, oh, should this be a float? I don't think this is gonna, this probably won't be it, but I will try. No. I'm sure in the comments you've already figured out what I've messed up. The bin height is height X, Y. I really have no idea what's going on here. What if I make this like 500? Will that like be better now? I don't think it will. So now it's drawing here and drawing downwards. So I think 20 or whatever was fine. And then the height is somehow upside down. I'm not sure why that would be. And that didn't work. Man, I'm gonna do the terrible, no, I'm not gonna print it. Oh man, do we have some like weird conflicting while loop somewhere? Well, just for fun, this will be upside down for now. I want to see if I make this smaller. We should get kind of a wider Gaussian. And yeah, it's looking wider. So I think this works. We did it. We made a Gaussian. It's upside down for some strange reason. I really would like to know why. We're starting here and then the height is the count. What if we just made this just to know where it's drawing? Just 20. Just to know where it's drawing. So it's drawing downwards. So if we make this 500, okay, it's drawing that way. If I make this 40, let's make it actually 100. Was it just drawing upside down the whole time? Oh, I think I know. So this should be, oh man. Yeah, okay. I think this should be like 500. And then we're drawing downwards. So it's like that way. The bin width. So if I make this, let's just double check 300. This should be somewhere in the middle of the screen. And then it draws downwards. If I make this 500, that should go like off the screen. Learning Raylib. Okay. So I don't know why it's upside down. I really don't. Is there like a different rectangle function I can use, or am I just bad? Let's use this one because I feel like I haven't had this issue before. The position is going to be bin X. Oh. Yeah, let's say bin X. Let's say let's say 500, and then the size is going to be bin width and bin height in gray. Maybe this, maybe I just made some dumb error. I don't know. That's still upside down. I don't know. I don't know what I've done, but in any event, there you go. What a crashing end to the video. That was kind of unfortunate. I was not able to figure that out. But in the comment, you can tell me what I've messed up terribly. But there you go, Gaussian random numbers. Thank you. Leave a comment.